Hi folks, on Friday's lab, I noticed that there is quite a few people who were missing because of a valid reason. And this being the case, and because this stuff is important, I'm going to prepare this video clip which explains how problem number 2 works. We are dealing with shell elements, therefore this problem has to be done with shells. You cannot do it as a solid object, okay? Uh, I'm not going to worry about the dimensions, but this folded sheet metal, the bottoms of these two edges are clamped, and this edge that you see here, this circular edge that you see here, is pushed in the y direction by some amount, which is 0.001 inch. Now, keep in mind that if instead of pushing in the y direction, we are pushing the circle downward in the z direction, there are two planes of symmetry involved. One like this, another one is the xz plane, the other one is the yz plane. However, I'm going to do it exactly like it's presented in this problem, pushing it in the y direction. Therefore, there is a single plane of symmetry, which is yz plane. All right, so let's go to Catia and do this problem. I did mention in the lab that there's two ways to do this problem. One is to create a solid object and extract the surfaces so that you end up with that particular shape of a folded sheet metal, or you can create the surface, the folded sheet metal, directly in the wireframe and surface design. I will go with the first method of extracting the surfaces, but there is a downside to that, and you will notice as I go along. I'll explain to you what the issue is if there is. This is the pathway you take. So let's go to Catia. We start with a part file, new, and a part. Okay. Now, because we're going to create a solid, we are in wireframe and surface design. Therefore, we switch to part design. On the XZ plane, we will draw the cross section of that solid. So it looks something like this, and we clean up the dimension in a minute. So something like that, like so, and there we are. We have to do some cleanup here. The left side control, right side control the middle axis. We make it symmetric. And let's make sure these radii are also the same value. I'm not going to worry about dimensions here. I think they are. If not, you just put a dimension here and make it the same value. So this is, say, 0.6, so that it's nice and round. And this one is also 0.6. And say OK. Let's exit this thing and pat it in the y direction by whatever we want. So let's say 4. Okay. Then on the top face, I will sketch that circle. And let's make it equidistant from the two sides. So top edge, control bottom edge, control the center of this thing, and you make this thing as equidistant. It's already exactly in the middle from the two sides, vertical sides. So exit, and we pocket this all the way to the end. That is to the end. Okay, good. And now we go to wireframe and surface design. So mechanical design, wireframe and surface design at the bottom. And in the operations toolbar, right here, the second icon consists of, the third icon consists of these two elements in it. This is not what you want. This says extract surface. Extract. So you do these things. You can do it one at a time if you don't pre-select it. So if you do, see that? It's going to extract that face. However, if I want to do them all at the same time, I have to pre-select it. Otherwise, it has to be done 5 times. So this, control that, control this guy, control that, and the final face, and then we extract. All of them are going to be done at the same time. It's just faster. And I can hide this solid part. So there is a solid part there which is hiding. You cannot delete that because the surfaces come from that. However, it's not the thing that we need. Anyway, let's apply material on this thing. Suppose this is made out of aluminum. So apply material, aluminum on that part, and OK. The downside of doing it like that is that these surfaces that are extracted are not talking to each other. If you want them to talk to each other and to have the same thickness, for example, you've got to join them. So here's the join icon, that face and this face, top face, this back curved side face, and the vertical face. Now they're joined. Okay. So one downside of doing it this way is that these faces have to be joined together. We now go to generative structure analysis. Catia sees a solid object in the background, in hiding. Catia sees this solid object, and as soon as it sees that, it's going to mesh this solid object, which is of no interest to us. Therefore, if you're doing it like this, make sure you go and delete the solid element and delete the 3D property that goes with it. So delete this, and don't forget to delete this 3D property also. Now, we have to mesh this thing with shell element. The shell elements are the same place that you find beam elements. So click on the shell. Because it's joined, they're all going to be meshed at the same time. And let's make it 0.3, for example. All right. If you want to see the mesh, right-click, mesh, and there is my mesh. Notice that there is no thickness because these are surfaces and these are shell elements. Okay, so deactivate this plot. Oh, you know what? I just realized that because there is a plane of symmetry here, I should have actually cut this thing before I meshed it like that. So let me close this analysis file back here, and you want to cut it with the YZ plane. So look for the saw in the wireframe and surface design, and read this thing carefully. It says element to cut is that surface. Cutting element is this plane, which is the, you can see right there, it's the YZ plane. And this is the face that we're going to, side that we're going to keep. All right, now we go to generative structural analysis. And the solid object that's in the background is meshed. We don't want it. So we delete this element. And also don't forget to delete the 3D property that goes with it. Okay, now we're going to mesh it with shell element. So make it a little bit smaller. How about 0.25? And okay. And if you want to see it now, mesh, and your mesh pops up. All right, let's deactivate this. The bottom of this is, you're told that it's clamped by the, yeah, okay, clamped. Oh, you know what? Why don't we apply the surface thickness now before we do the clamp? We can wait until apply this before. We can do this after we apply the restraints, but I'd rather do it now before we forget. So here's a 2D property where the model manager is and the traffic light is. So 2D property, select that and put the thickness that you want, say 0.1 inch. Because these are joined, they all have the same thickness. If they are not of the same thickness, you cannot join them. And I'll do that in another video after this. All right, now let's clamp the bottom. You're told that this bottom is clamped, that entire edge is clamped. And now we apply symmetry conditions. See this edge, and the one next to it are in the plane which is parallel to YZ. So we do user-defined restraint. The rules are just like what we did in the beams. In other words, these two edges first you select. These two edges lie in the YZ plane as a plane of symmetry. Therefore, they don't move in direction X, and rotations are opposite. So because this is checked, its rotation is free. These are unchecked. Translations are unchecked, so their rotation must be checked. All right. The entire circular arc is pushed in the Y direction. So in Catia, you know that in order to apply a non-zero displacement, first you give it a zero displacement and then you change it. So this circular edge not the vertex, that entire edge. And notice that the vertex is also selected here. The easiest way is just cancel that, do it again. Because accidentally I selected that vertex, which is halfway on this arc. So this entire edge, it sits in the YZ plane. This is being pushed in the direction Y. So you give it a 0 displacement in direction Y. You can see that. Say OK. And then you go to enforced displacement and change that to a non-zero value that you want. If you are having a hard time picking it from screen, you can do it from the tree. And now you give it a 0.001. I also noticed that there is a 0.001 inch left over here. And this is because from my previous run, I had this number sitting there. So you know what? Let's cancel this thing one more time. User-defined restraint. Select that. This is the one, right? Okay, that's good. 0 displacement in the Y direction, and then enforced displacement. And let's zero this out because we want to push it in the Y direction. So this number was sitting there from my previous run. I made it 0, and then I make this thing 0.001. That's it. So let's run this thing and see what happens. What's going on here? My guess is that there's some stuff that I forgot to delete now. So to say no, it won't run anyways. Under loads, let's see. This is okay. So there's something else that is causing a problem here. Let me double click on this. This is fine. There's no problem. All right. You know what? I have to bite the bullet and fix this thing because I don't know exactly what's going on. Let me delete this. Okay, try it again. Enforce displacement, delete it. Sometimes this is the easiest way of fixing things. User defined that edge in the direction Y is 0. Good. Now apply enforced displacement to that restraint and 0.001. Okay, I'm hoping that this will work now. All right, let's go ahead and run it. Yup. There was no sense in trying to find out what's going on. It was easier if I repeated it. Okay, good. It's done. So let's look at the deformation. This is how it's going to deform. Believe it or not, that's how it's going to deform. And notice that this is all a straight line on the plane of y on the plane of yz, because yz is a plane of symmetry. Okay, and then you can look at the von Mises stress and change the rendering. This is how it's going to behave. I showed you the steps. It doesn't mean that the numbers that we get are meaningful, although they're not that bad. But I'm just showing you the steps. The rest of it is your engineering judgment and see whether this von Mises test, for example, makes sense or not. Let me see, what else do I want to tell you here? Okay, so let me stop this for a second. Let me stop this. And we can animate it, obviously. This is what's going to happen. If you could push the circle in the y direction, all the points on that semicircle in the y direction by 0.001, this is how it's going to look before. I want to show you an alternative way of doing exactly this same problem. Instead of going to the solid elements, we can do it directly. So let me close this thing, and I'm going to close that. Okay, let me start a new part file. So this time we are not going to create the solid object. because remember, we had to go and delete the 3D element and 3D property. So on a convenient plane, say this vertical plane, we will sketch. We are in wireframe and surface design now. So I'm going to do the following. I'm going to create the profile of that sheet metal, which looks like this. And let's clean it up. So the left edge, control right edge, control the middle axis. Let's make it symmetric. And these have to have the same radii. So why don't we dimension it? So let's make this thing 0.8. And let's make this thing 0.8. Exit. That's how it's going to look like. Whoa. Okay. Okay, this is playing tricks on my eyes. Okay. And then extrude this to the extent that you want. Say, I don't know, 4 inches, for example. No solids here. This was done directly in wireframe and surface design. There's nothing hiding there. I didn't make a solid. So on that top face, I will sketch. Let's see now. I sketch the circle that I want exactly in the middle. And if you want to make sure it's in the middle, top line, control, bottom line, control, that center, you make it equidistant. Exit. And now I want to drill a hole up here. So look for the saw and read this thing carefully. It says element to cut is that surface. Cutting element is that circle. There is the hole. And because of symmetry, we said that we want to cut this thing in the Y direction. So once again, get the split, read it carefully. Element to cut is that surface. And the cutting element is that plane right there. And let's say we want to keep the other side. Okay, there it is. And we cut it. We can hide these things. These geometric things, they don't participate in the FEA. So I'm going to hide that, and I'm going to hide this. Okay. Now, there's no reason to join, because the way it's done, it's all a single sheet metal. These sides talk to each other. Okay. And let's apply material to it. So where is apply material? And let's make it out of metal, aluminum on that part. Good. We now go to generative structure analysis. Catia immediately sees a surface, but surfaces, unfortunately, it doesn't mesh. Beams don't mesh automatically, so we have to mesh that ourselves. These steps are identical to what we did before. So surface mesh or shell mesh, put a number that you want, say 0.2. Say OK. You want to see your mesh, right-click, mesh. There it is. Now deactivate this mesh, or delete. I just accidentally deleted it. That's fine. So we want to clamp this bottom edge. And let's see now. These two edges, this edge and that edge, are in plane of symmetry. So user-defined restraint, uncheck these things so you start fresh and don't make a mistake. That edge and this edge, it lies in the YZ plane. There is no displacement in direction 1, direction X, and rotations are opposite. So this takes care of plane of symmetry. Then we want to take this circular arc and push it in the Y direction. So first you make it 0. So that arc doesn't move in the direction 2. But that's exactly what we want to do. We want to make it move. So, but you have to make it 0 first. And then enforce displacement. If you're having a hard time picking it from here, let's go to the tree and select that restraint. Okay? And 0.001. Okay? What's missing here is the thickness of the shell. So we go to 2D property, select that, put the thickness that you want and say, okay. These are all identical steps to before. To what we did before. The only thing is that we didn't have a solid element to delete the mesh, and let's run it and see what happens. There we are. It's going to work. And if you plot the deformation or Van Mises stress, it's going to look exactly like what we had before. There. Okay? It's hard to believe, but if you were able to push the circle, every point of that circle to the right by 0.001, this is how it's going to look. All right. So we did this in two different ways. And I'm done as far as this video.